ICSE warriors. I'm glad to see you back on my channel. My name is Prachi Sharma, and in today's session we will be working on the chapter Ammonia, that is chapter 9th of your chemistry syllabus. So without wasting any time, let's get started. Alright students, I hope my screen is clearly visible to you. Now, whatever we cover in this chapter today is highly important. Other than whatever is happening in this session, you don't have to do anything else for this chapter. If you are thorough with the concepts which we are discussing today, your chapter is good to go for the exam. After the session, I would include this PDF file in the comment section or in the description box, so you can check that out from that point. Okay, let's get started. Now, what is ammonia? Ammonia is a gas. How does that smell? It is a pungent smelling gas. Okay. Now, where do we generally find this gas? Now, if you would have used any public restrooms or even sometimes in our own house, when you go to the restroom, the smell is pretty weird. That pungent smell is of ammonia. Why does a bathroom or a restroom smell of ammonia? That is because ammonia is produced on decomposition of urine. Okay, so when urine is decomposed, ammonia is secreted, and when ammonia is excreted everywhere, so the smell of course becomes pungent. So pungent smell at decaying heap of organic matter or washroom is due to ammonia. It is produced due to bacterial decomposition of urea. Okay, how can you remember the formula for urea? NH2 on both the sides, and in the center you have a CO. So NH2, CO, NH2. Moving on to the occurrence of ammonia. In free state, ammonia is present in small amounts in air and in traces in natural water. In combined state, ammonia occurs in combined form in many compounds such as ammonium chloride, ammonium sulfate, etc. It is produced due to bacterial decomposition of urea present in urine. So you have urea here. In the presence of moisture or water, it decomposes to ammonia, water and carbon dioxide. Now, what are the various forms of ammonia? Another important thing is that while going through this entire PDF file, whatever equations are important for you to learn, I would help you mark them. So I'll keep marking as we move on. Other than those equations, you don't have to learn anything else in equations. Moving on to forms of ammonia, we have the gaseous form, that is your dry ammonia gas. Liquid form is when ammonia is liquefied by applying high pressure, is called liquid ammonia. So you have a gas in a container, you keep providing pressure from the top, and eventually due to the pressure it gets liquefied. So that is liquid ammonia. Moving on to liquor ammonia fortis. So liquor ammonia fortis is not like the actual liquor that you can think of. Okay, it is a saturated solution of ammonia in water. So ammonia is highly soluble in water. When we keep combining it into water, a point comes where no more ammonia gas can be dissolved in water. Such a stage is known as liquor ammonia fortis, the saturated form of ammonia. It is called 880 ammonia. So you should know the other name. So the first name is liquor ammonia fortis. The other name is 880 ammonia. Moving on to laboratory bench reagent. Dilute solution of liquor ammonia is used as a lab reagent. So the ammonia gas or the ammonia form that you would find in the labs would be your laboratory bench reagent. Then preparation of ammonia gas. In general methods of preparation, you have ammonia gas. How will we prepare that? You have ammonia salt. You react it with an alkali, and that gives you salt plus water plus ammonia. So ammonia gas can be prepared by warming an ammonium salt with caustic alkali such as slaked lime or caustic soda or caustic potash. Now what is happening here? Ammonium salt is reacting with an alkali, giving us salt plus water plus ammonia gas. If you do not remember these equations, you can form your own equations. You just have to remember that you have to pick one ammonia salt, combine it with an alkali, and that will eventually give you salt plus water plus ammonia. So ammonium salt we have is ammonium chloride here, combining it with calcium hydroxide, giving us calcium chloride, water and ammonia. Similarly, you have other salts. You can go through these. If you have any doubts in any of the equations, make sure that you leave a comment in the comment section. I don't mind making a separate video just of equations and discussing how to learn them. Moving on to the second method, we have the lab preparation of ammonia gas. So from ammonium chloride, this is the lab setup. Now, if you see here, these are ammonium salt. So ammonium chloride is present here. This is ammonium salt and calcium hydroxide is reacting with it. So both of them are combined together. Then you are providing heat to the apparatus. Once you are providing heat, the gas starts coming down from this particular angle. So we'll come to the reason why we are tilting it to an angle. So ammonia gas starts coming out from here. But as per the equation, we remember that water is also produced. So that means this ammonia gas must be moist or would be carrying some water along with it. So to get rid of the moisture, we are using quicklime to dry the gas. So this gas will eventually pass up. It would go up. This is quicklime. This will end up absorbing any moisture from the gas. It will move up and eventually reach up in this apparatus where it is collected by downward displacement of air. Okay, let's look at the equation. This is an important equation. Now, ammonium chloride combining with calcium hydroxide, giving us calcium chloride, water and ammonia gas. Now, the reagents that we are talking about, or the reactants that we are talking about here, are taken into a ratio that is 2:3 by weight and finely grinded. Why are we taking finely grinded? So that maximum output can come. You have a better reaction going on. 2:3 in the ratio. That means if you have 2 portion of ammonium salt, then 3 portion of alkali. So 2:3 by ratio. What are the precautions? Now, the flask is tilted in such a way that the water formed in the reaction does not trickle back into the heated flask and thus break it. Now, if we come back on the diagram, we saw that the flask was tilted. So when the ammonia gas is going, along with that water is also going. Now, if you have the flask right, straight up, the water can come back and trickle down into that very high heated flask. What would happen then? The flask may break because of different temperature, because of water cooling down and coming down into a hot flask. Now, drying of ammonia gas, it is dried using quicklime. They can ask you a question, they can give this diagram, a diagrammatic question, or they can say the following questions are based upon the lab preparation of ammonia. They can ask you the equation, they can ask you what precautions you are taking, they can ask you what is the drying agent used in the process. Now, concentrated sulfuric acid, phosphorus pentoxide and calcium chloride reacts with ammonia, so they are not used. Why do they react with ammonia? They react with ammonia because ammonia in nature is an acidic gas. So, and is an alkali gas. So what happens is that when you have sulfuric acid, phosphorus pentoxide, so for example we take sulfuric acid, it's an acid. Ammonia is alkali in nature. So when these two combine, instead of drying the gas, sulfuric acid will end up reacting with the gas. So your purpose of introducing sulfuric acid is lost. There is no point in putting sulfuric acid there. So that is the reason you do not use any of these reagents, because ammonia is an alkali gas. It ends up combining and reacting with these agents. Now, collection. It is collected by downward displacement of air. Why is that? Because it is lighter than air. And why we don't use water? Because it is soluble in water. Okay, I hope this much makes sense. Alright students, moving on to the second part of our lab preparation. This is from metal nitrides. So we have the setup here, you can see. So we have water, warm water that you can see in the thistle funnel, that is right here. It is being brought down like this. Then you have magnesium nitride. You have the drying agent here. Now let's see what is happening. We have the water being introduced to magnesium nitride very slowly, drop by drop, and this water is warm water. So warm water is introduced with reacted with magnesium nitride. As it is reacted, you get ammonia gas. This ammonia gas would go up from this flask, from this funnel, from this tube, and then move ahead and end up in this container. Eventually it would rise because of course it is lighter than air. It would start rising up. Drying agent quicklime will take up extra moisture and the gas is easily collected in this jar over here. Okay, now let's look at the reactions. Magnesium nitride reacting with warm water, giving us magnesium hydroxide and ammonia gas. Now, what are the precautions? There are no specific precautions in this, but you need to understand that warm water is added slowly, which produces magnesium hydroxide and ammonia gas. The drying agent used is again quicklime. Moving on to preparation of aqueous ammonia. What do we mean by this? We try to understand how do we mix ammonia in water. Now, this is the same process, that is the inverted funnel arrangement. This is the same process that we did in HCl gas also. If you are not able to follow in this one, you can quickly go back on the HCl video and just check out the detail that we discuss in that. Now, when you try to understand the mixing of ammonia gas in water, don't focus on this apparatus, okay? It's fine. Ammonia gas is being liberated, we understand that. What you need to understand in this part of the chapter is how is it dissolved in water. So you have the inverted arrangement like this. The ammonia gas is coming in. It is in the beaker. We have water till this part. Okay. Now what happens is it is just touching the top of the water surface. Now, since ammonia gas is highly soluble in water, it would quickly dissolve up into the water and the water will be sucked up into the apparatus. So the water will come up here in the entry level, and because of the weight, it would again fall down. And the gas would again come in, dissolve, the water would come up and then fall down. Now, why do we specifically use this particular arrangement and not the regular tube one? The reason is that as the water is highly soluble in the gas, the production of the gas is not that high compared to the solubility of the gas. So because of the vacuum that is left up in the tube, the water will eventually start rising up into the tube, and eventually it may end up getting interfering with the actual arrangement of the preparation. So that is the reason we never use the regular tube arrangement. We use the inverted funnel arrangement. Larger surface area, so the water would rise up and then fall back down. Okay, so this is your aqueous preparation of aqueous ammonia. Moving on to the manufacture of ammonia, that is by Haber's process, very important. Now, if you look at this apparatus, let's look at the apparatus and try and understand what's happening. So you have nitrogen from liquid air, hydrogen by Bosch process, 1:3. So 1 volume of nitrogen is going, 3 volume of hydrogen is going. Then you have a compressor right here. Then you have a recirculation pipe. Both of the gases are coming in. Then you have a catalytic chamber. In this you have the catalyst at 500 degrees Celsius. The atmospheric pressure is 250. Then you have the cooling chamber. In the cooling chamber, the gas is cooled. Then whatever is left or uncombined gas goes back up into the entire process. Okay, we'll go into the detail of every part. So for now, just understand what is happening in the process. 1:3 by volume, nitrogen gas and hydrogen gas are introduced in the apparatus, goes into the compressor, moves ahead into the catalytic chamber where the catalyst is kept at 500 degrees Celsius and 250 atmospheric pressure. Once that has happened, your reaction has happened, completed, move on to the cooling chamber. Because the temperature was very high, you need to drop the temperature when you move into the cooling chamber. Whatever gas is formed, the liquefied gas, would move on into cooling liquid in. This is the liquid that's coming in and it's like cooling it out. Whatever gas is your liquid ammonia, it would go out of the apparatus and all the uncombined gas will go back into the apparatus and start the process again. So in this way, we do not waste any gas that we are using. Highly important process. Moving on to the sources of the reactants. So nitrogen gas is obtained by fractional distillation of liquid air. Hydrogen gas is obtained from water gas, that is by Bosch process or natural gas. The reaction is very simple. Nitrogen combined with hydrogen gives you ammonia plus heat. Plus heat, that's why we are using the cooling chamber. This reaction is exothermic, reversible and proceeds with decrease in volume. Moving on to favorable conditions, we saw that the catalyst was at 500 degrees Celsius, but the reaction can still happen at an average of 450 to 500 degrees Celsius. So the temperature can range about that. The pressure can be about 200 atm. Then catalyst is finely divided iron. Very important to remember. Catalyst is finely divided iron. Promoter is your aluminium oxide, that is Al2O3, or molybdenum. Okay, any of the promoters can be used. Now rate of conversion. About 15% of the reacting gases gets converted into ammonia. Whatever is left out goes back into the process. Now recovery of ammonia. Ammonia is separated from the unreacted nitrogen and hydrogen by liquefaction. Ammonia is liquefied easily as compared to nitrogen and hydrogen. Absorbing in water. Because ammonia is highly soluble in water, while your nitrogen and hydrogen are very slightly soluble in water, so it is easy to keep them separated. Now, process. Step 1 is nitrogen and hydrogen are dried, purified and then mixed in the ratio 1:3 respectively at a relatively high pressure. So when nitrogen and hydrogen enter our apparatus, we have very high pressure there and they are in the purified and dried form. So you do not have any moisture entering the process. Step 2. This mixture is passed in an electrically heated catalytic chamber containing finely divided iron with aluminium oxide or a little amount of molybdenum at a temperature of 500 degrees Celsius. This is very simple things written. After entering into the apparatus, it eventually came in the catalytic chamber. Now what is the catalyst we are using? We are using finely divided iron. We are using molybdenum. We are using aluminium oxide, and all of these are at an average of about 500 degrees Celsius. Step 3. Mixture of ammonia 15% formed along with residual nitrogen and hydrogen exchanges their heat with the incoming unreacted nitrogen and hydrogen mixture. So it was that the simple thing that they mean here is that 15% of your ammonia and along with that nitrogen and hydrogen is left out. Step 4, the mixture is passed through the cooling pipes. So this mixture is gone through, it goes through a condenser. Ammonia liquefies first, whereas nitrogen and hydrogen do not liquefy easily. So they go back and the liquefied ammonia would come out from the pipe that is at the bottom of the apparatus. Step 5. The unchanged nitrogen and hydrogen get recirculated through the plant to get more ammonia. So the unchanged nitrogen and hydrogen are recirculated. By recirculating in this way, an eventual yield of 98% can be achieved. That means we are not losing the gases that we are using as reactants. About 98% of success in getting ammonia is obtained by reusing the gases again and again. Now, the note. The reaction is exothermic, hence low temperature will favor the synthesis. However, at low temperature, the reaction proceeds slowly. So, the optimum temperature is 450 to 500 degrees Celsius. 4 volumes of reactants produce 2 volumes of the product. Hence, high pressure favors the formation of ammonia. Optimum temperature to be maintained is 200 to 900 atmospheric pressure. Catalyst and promoter, of course we have done, you have finely divided iron, then obtained by reduction of iron oxide. Then a promoter would be aluminium oxide or molybdenum, is used to increase the efficiency of the catalyst. Number 4, since the reaction is exothermic, the heat evolved further maintains the temperature. So what do they mean? They do not keep giving in the heat. As the reaction proceeds, the heat that was evolved is eventually used in the proceeding of the reaction further. So you do not need to keep giving it heat. It is a sustainable reaction. Whatever heat is produced, it continues the reaction further. External heating is therefore not required after the reactants are initially heated. Now, the purification of nitrogen and hydrogen is necessary as impurities like carbon dioxide, carbon monoxide and traces of sulfur compounds poison the catalyst. Okay. The removal of these catalytic poisons from nitrogen and hydrogen is very essential. This is an important one. When they ask you the questions based on Haber's process, they can ask you why is it necessary to get rid of the impurities from nitrogen and hydrogen. The answer is that it contains impurities like carbon dioxide, carbon monoxide and traces of sulfur compounds which can end up poisoning the catalyst. Hence, we need to avoid the presence of it. We need to have purified gases. Now the flow chart of the Haber's process. This is important for the exams. Like you can, before going for the exam, you can quickly take a recap from this flow chart. Nitrogen and hydrogen entering the chamber. Compression pump is, increasing the pressure on the reactants. Moving on, you have electrically heated catalytic chamber. The catalyst would be finely divided iron, molybdenum. Then you would have, you can have aluminium oxide. Then you have condenser with cooling pipes. It tries to condense the gas that is formed or the entire output products. 15% of ammonia that we get is the liquid ammonia that comes out. Rest, everything goes back into the process. What is the equation? The equation is this. Your conditions are this. Need to remember all of them. Okay. I hope this much was, easy to understand for you. That was the Haber's process. Highly important. Now, physical properties of ammonia. Ammonia is a colorless, odor is pungent and choking. Taste is slightly bitter. Why bitter? Because of course it is alkaline in nature, so bitter in taste. Now, it is non-poisonous. If inhaled, affects the respiratory system and bring tears to eyes. It is a powerful heart stimulant and may cause death when inhaled in large quantities. So it is not poisonous, but if inhaled in large quantity can stimulate heart and affect our heart functioning and can cause death in that situation. You do not have to remember all the physical properties. The only things you have to remember is the color, the odor. Then you need to remember, you don't have to remember the density. The nature is alkaline, nature you should remember. Then liquefaction, so it is easily liquefied at 10 degrees Celsius. I'll just mark the ones you need to remember. You need to remember the color, the odor, the taste. You need to remember the nature. Rest you don't have to remember. You can remember the solubility also. So liquefaction, easily liquefied at 10 degrees Celsius by compressing it at 6 atm pressure. Now boiling point, just go through these points, nothing that you have to remember. Now moving on to fountain experiment. Now fountain experiment, if you have done HCl, you would remember from that fountain experiment was an experiment to tell us that HCl gas was highly soluble in water. We are doing the same thing here. So you have fountain experiment to demonstrate that ammonia gas is highly soluble in water. Now let's see. So this is the setup. This contains your red litmus solution. This flask contains dry ammonia. Now here is a dropper. Okay, now the dropper has water in it. Okay, this bulb of the dropper. As you squeeze the dropper, a couple of drops would enter from here. They would enter into the apparatus. So a couple of drops of water would come in. As soon as a couple of drops of water would come in, ammonia would quickly dissolve in water. What would that give us? That would make a vacuum created over here. You'll have a little bit of vacuum created. To cover up that vacuum, this red litmus solution would suddenly be rushed up because of that vacuum to cover up the space. And as soon as red litmus solution enters, it reacts with the, because of the presence of ammonia, it gives us a blue fountain. So red litmus solution was entering in, presence of ammonia changes it to blue, and you see a blue colored fountain. Hence we call this a fountain experiment. So over here you can see a blue fountain. Let's read about it. A bottle of liquor ammonia should be opened very carefully. So okay, so you do not have details about this. You do not need a lot of details. Now, a bottle of liquor ammonia should be opened very carefully only after cooling it in ice or cold water. Why is that? Because when we cool ammonia, it has a very high pressure. So when it becomes warm and you're trying to open it, the pressure is trying to get released from the bottle. So there is high pressure inside the bottle of ammonia, and on cooling the pressure drops. This prevents sudden flushing out of the gas. So if you have the heated up bottle and not the regular bottle, the pressure would try to flush out of the bottle very quick. So accidents may happen, you may get hurt. But if you try to cool it down first and then open it, the pressure would drop because of the drop in temperature. Okay, the pressure will become more easier for you to handle, and then you can open up the bottle. Moving on to chemical properties of ammonia. So the first is thermal dissociation. You heat up ammonia, you get nitrogen and hydrogen. Basic properties. So dry ammonia is neutral in liquid form. Now, why is it neutral in liquid form? Because there is lack of moisture present. If they ask you what kind of color change will dry ammonia show, it won't show any color change because dry ammonia is neutral because of lack of moisture. Aqueous ammonia is a weak base due to the lone pair of electrons on its hydrogen atom. Okay, now let's see. So ammonia combining with water will give you ammonium hydroxide. Third property is burning of ammonia in oxygen. Ammonia is not a supporter. Okay, it extinguishes a burning splint and does not burn in air. It burns in oxygen with a greenish yellow flame. Why do we say it burns in oxygen? This is excess oxygen that is being provided. Okay, just pure oxygen, nothing else. So what would happen? You'll get a greenish yellow flame here. Very important question, it is asked a lot. So ammonia when reacting with oxygen would give you N2 and H2O, and this burns with a greenish yellow flame. This reaction is irreversible and strongly exothermic. It shows ammonia contains nitrogen and hydrogen. Okay, very important point. Moving on to the fourth, that is catalytic oxidation of ammonia. In the presence of platinum at 800 degrees Celsius, ammonia reacts with oxygen to give nitric oxide and water vapor. Ammonia gas reacting with oxygen in the presence of platinum at 800 degrees Celsius gives us water plus nitric oxide. This nitric oxide would further react with oxygen and give you NO2. You can see the diagram right here. So this is the portion where you have the platinum catalyst. You are providing heat to it. Dry ammonia is being entered from here. Dry oxygen is coming in here. And of course, further you see water droplets being deposited in this part. Moving on, you would have the gases coming out. So NO plus O2 would give you NO2. NO2 is collected here and eventually collected in a different apparatus. Alright students, let's move on to the fifth point. That is ammonia as a reducing agent. So what does ammonia would do? If you have a metallic oxide, ammonia would react with a metallic oxide, give you a respective metal, water vapor and nitrogen gas. So this is reducing action of ammonia. Now let's look at the apparatus. You have copper oxide right here. Dry ammonia comes in, reacts with copper oxide. Eventually you have water vapor and nitrogen gas moving forward. This cold water trough, this will end up condensing the water vapor and you have water being collected right here. Whatever nitrogen gas is left out, it will move ahead and be collected right here by downward displacement of water. Now let's look at the details. Reduction of metallic oxide by ammonia. So ammonia reduces heated metallic oxide to metal, water vapor and nitrogen. Okay, let's look at the reaction. Ammonia reacting with CuO, that is a black solid, giving you copper, that is a reddish brown solid, water and nitrogen. Then reduction of chlorine to hydrogen chloride. So if you have ammonia reacting with chlorine, it would end up giving you hydrogen chloride. So reduction of chlorine to hydrogen chloride. When chlorine reacts with ammonia, it reduces to HCl, which further combines with excess ammonia and forms NH4Cl. Okay, so you have the equation right here. When ammonia is in excess, ammonia, chlorine gives you nitrogen N2 plus NH4Cl. When chlorine is in excess, you get ammonia, chlorine, HCl and NCl3. What does this show us? This shows that chlorine has a very high affinity to hydrogen or for hydrogen, or it won't let it go. So it has a high affinity for hydrogen. And ammonia is a reducing agent. Okay, now let's look at this point again. Very important point. All right, so you had ammonia and it is reduced, like reduction of chlorine to hydrogen chloride. So when that happens and you have excess of ammonia, in that form you get NH4Cl, because whatever reduced HCl you had would end up further combining with excess ammonia to give you NH4Cl. When chlorine is in excess, you end up getting HCl and NCl3. They can ask what kind of question they can ask. They'll say, give an example, or how would you prove that chlorine has great affinity for hydrogen with the help of an equation? So you should be able to give this equation. They can ask you an example to say that how would you define that ammonia is a reducing agent with the help of an equation. So you can take up these equations, or you can take up this equation, the copper oxide equation. Then moving on to reaction with acids. So ammonia gas itself is a weak base. So it ends up reacting with acids. So ammonia being a weak base accepts protons, okay, that is your hydrogen ions, to form ammonium ions. When these ammonium ions are formed, they end up reacting with acids. So, it reacts with acids to form ammonium salts. Ammonium chloride is a good example where two colorless gases react to form a white solid. Very important. Okay, two colorless gases react to form a white solid. The gases they are talking about here is HCl gas and ammonia gas. They can also ask you, give an example where an acidic gas and a basic gas gives you a solid. Okay, so that is what is happening here. You have ammonia gas and chlorine gas giving you a white solid. I hope this much is clear, students. Let's quickly move on. Ammonium nitrate and ammonium chloride both show thermal dissociation. That means provide them heat, they will break down into corresponding compounds. NH4Cl would give you NH3 plus HCl. NH4NO3 would give you N2O plus water. Aqueous solution of ammonia. Ammonia is dissolved in water to form aqueous solution. So NH3 plus water gives you NH4OH, ammonium hydroxide. Ammonium hydroxide reacts with acids to form salt and water. Ammonium hydroxide reacts with acids to form salt and water. Reaction of aqueous solution of ammonia with soluble metal salts. So ammonium hydroxides react with soluble salts of metal to give insoluble precipitates of their respective metallic hydroxides except sodium and potassium. So except sodium and potassium, you have to remember that. This behavior is similar to NaOH solution. Students, read through this and let me know in the comment section if you think you're able to understand or if you have any doubts in this. Make sure you go through it again and drop a comment in the comment section. Moving on to the last portion of the chapter. Students, you have done a great job so far. Let's go through the last section, that is test of ammonia gas. Now, it has a sharp characteristic odor, pungent smelling gas. You can quickly say it's ammonia gas. Second, it's a weak base, so it will turn your red litmus paper to blue. Moist red litmus to blue. Okay, phenolphthalein would turn pink. So sharp colorless odor. It turns moist red litmus blue. Then you have the moist turmeric paper brown. Phenolphthalein solution would turn pink. Now, it gives dense white fumes with concentrated HCl. So ammonia reacting with HCl will give you NH4Cl, that is your dense white fumes. Fourth part, when ammonia gases pass through copper sulfate solution, blue PPT is formed which changes to deep blue solution on passing the gas in excess. So ammonia gas passing through copper sulfate solution gives a blue PPT. If you continue passing the gas, that turns into deep blue solution because the precipitate will eventually dissolve. Okay, so it will turn into a deep blue solution. All ammonium salts generally produce ammonia gas when warmed with alkali like sodium hydroxide. Last point, ammonium salts give brown color or PPT with Nessler's solution. Okay, what is Nessler's solution? K2HgI4. Okay, Nessler's solution is K2HgI4. A slightly alkaline solution of potassium mercuric iodide made by adding KOH. So ammonium salts will give you a brown color. Okay, by what? Nessler's solution. What is Nessler's solution? K2HgI4, that is potassium mercuric iodide. Okay, so that would conclude our chapter right here. All right, students, this is the end of our chapter and the end of our today's session. You were amazing today. You did a wonderful job going through the entire chapter and understanding each and every concept. I would still say that if there is any part of the chapter that you are still struggling with, Any question that you can't answer from ammonia yet, drop a message on the comment section and I will help you out. Now, moving on, I would like to suggest that as we are going along the videos, make sure that you are downloading the notes from the description box. If you would like, you can print them out. If you would like to go along the video and mark yourself and write your own notes, whatever works for you, I do not mind that. Along with these, we would eventually be coming on the test papers, discussing some important questions, and I have already uploaded a video of ammonia questions that are important and the ones which we have seen in the past board exams. Thank you so much, students. Let's catch up in the next session. Thank you. Have a good day.